Number 24, zoop, 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 zoop. They gave it to you in radians, but they also gave it to you in degrees, so they're kind of indicating like, hey, we don't care what mode. This one didn't matter, this one does, because that angle was given to us in radians. There was no degree mark. Quick refresh. Number 28 was one of those rise over run, y2 minus y1 over x2 minus x1. Square root of 3 over 3, 1 square root of 3. That's a 60-degree angle. 60-degree angle is going to be, well, it's negative though, so second quadrant, 2 pi over 3, or 120. But if you plugged it into your calculator, you would have gotten negative 60 or negative pi over 3, and that would not be right because inclinations are always positive. We look up to the mountain, not go digging in the ground to follow the line to find the angle. Awkward. Number 52, you guys should have found your m's. By rearranging, getting y by itself, just like we saw yesterday, the easiest way for angle between, throw it in your m2 minus m1 all over 1 plus. Wait a minute. Order does matter. There's a minus. Bummer, man. Or does it? Oh, there's an absolute value. It doesn't matter. Anyway. So in a way, it looks like it matters because subtraction is not commutative. I wrote that plus yesterday, and so my explanation was a little bit off. But even though I wrote plus and said, oh, commutative doesn't matter. Absolute value says, okay, whichever way you subtract it doesn't matter. A positive will stay the same. A negative will become a positive. Same answer. But wait, 15/8 was not the answer. You were looking for the angle, and to find the angle, what did you have to do to both sides? Got him, coach. 61.9 or 1.0808. Wow, that was way more decimals than most of you would have put. Gavin.
For the top equation on 52,
yeah.
How does m1 get to be 3 over 2 when it's 3 over 5x minus 3 over 5?
Oh, was that the actual? I didn't even look and compare. I totally disagree with that. What do you guys have for, do you have the exact same equation, 3x minus 5y is 3?
It's right in the, when you plug it in.
Oh, good catch, Gavin. It's a typo. Do you see it? No, yeah.
I was reading from top to bottom.
No, you're good. Thanks, guys. Gavin, thanks for pointing it out because some people might have written it and then been so confused later. But down here, yeah, it was totally good.
So the formula
is m1 minus m2 all over 1 plus m1 m2. But to be honest, the order doesn't end up mattering because of the absolute value. Do we have more evens? Oh, we don't. All right, cool kids. Do we have any questions? Odds or evens on 10.1? Going once. Yeah. 24. Anything else besides 24? Robbie, what are you saying over there? What section are we? 10.1, right? Okay. Bloop, bloop. Ooh, look. It's a light bulb and a parabolic reflector. Interesting. Oh, conic sections. What was weird about 24? Where is 24? Well, Gavin, 24 is going to be a non-unit circle value. And I'm saying non-unit circle because in order to find inclinations, guys, real quick, the formula from section 10.1 that relates slope to inclination. So I would plug in negative 7/9 is equal, if this was a unit circle one, square root of 3 over 3, 1 square root of 3. I would jump to the answer, but since it's not, so then we just take, remember to undo a trig, we do a trig inverse. Theta equals, now, here's the dilemma. When you do this in your calculator, which you have to do, you can't do unit circle, Bobby, focus. When you do this in your calculator, which you have to, it's going to give you a negative angle. It's going to give you a negative angle. But as it gives you a negative angle, actually specifically tangent one, pretty close to pi over 4, so I'm going to put ish. Remember my little illustration? Why do we want a positive inclination? If this is the ground, just a silly illustration. If this is the ground, and that's the mountain, okay? I want to know how steep the mountain is. I want this angle. I don't want to go digging in the ground to find them out and continuing and then be like, oh, what's that angle? No, I want that angle. So if the calculator gives me, when I do tangent inverse, if it gives me a negative angle, whatever that negative angle may be, I'm going to say, no, I'm adding 180. Remember, we can always get to the other side. We can always get to the other's perspective by adding 180. Or if you're in radian, careful what you add instead. Got him. Which is why in our answer key, when you go to look at it, this is the one I warned about. I said your calculator would have given you a negative answer. So you have to add pi, which they then converted, or you could have added in degree mode 180 and what would have gotten there. Does that make sense though? Okay. Yeah, and it's not that the negative is wrong, it's just a perspective. We don't want to go looking down there for it. We always want to be looking up for it. Yeah. Okay, anything else on homework? Going once? Going twice? Sold. A lot of us are writing. I'm not sure what we're writing, but anyway. Okay. If you guys want, you can quickly write down section 10.2 homework. Zoop, zoop. Because some of you are writing down something or others. Maybe you're in Google Classroom getting down the next homework. We're going to go back to our notes. Zoop, zoop, zoop. But there's section 10.2. Or you can just grab a picture of it, or you can get it from Google Classroom tonight. I think I updated your Google Classroom and it's already been posted. Do you guys agree? Yes. Any of you that check your emails? Yes. Okie doke. All right, we are going to analytic geometry. Boop. Okay, everything to do with conics. However, let's just get this on the table now. Whenever I cover something that can be done in the calculator in some way, shape, or form, do I show you how to use the calculator? Yeah, which is why for many tests, haven't we had a calculator, non-calculator portion? I showed it to you with sigma notation and summations. I showed it to you when we were doing matrices, multiplication, inverses, determinants, RREF, row reduced echelon form. When we were doing, what else have we been doing with calculators? Things with trig. I have to teach you how to use your calculator because like the one that Gavin just asked about, the calculator gives you one answer. It's not actually the appropriate representation of the answer that we wanted, etc. So I show you the pitfalls. I show you the times. Didn't we do one? Oh, we didn't. Precal did. I had them trying to use their calculator in sequence mode to like find the 1,000th term, and the poor little calculator was like, nope, timeout. I'm not doing that for you. So our calculators are only so strong. They're not like a supercomputer, or even as strong as a normal computer. Although I guess they're probably stronger than the computers that filled the rooms like 50 years ago. Anyway, which is kind of crazy to think about. But our calculators can do a lot. I want you guys to go under your apps button. Your apps button. Sadly, it's only the newer calculators, which is everybody but one of you. But the apps button. If you don't have your calculator, look on with your group. I want you to look through the apps, the applications, the extra special programs, and find something that applies to this chapter and specifically this section. And I want you to explore. Yep, I want you to explore. What is in there? What options are there? What can you do? What can you select? What can you plug in? AP Chem kids relate, but you guys aren't AP Chem kids. You're looking around, you're exploring, you're seeing what it can do. You're seeing, can it graph stuff, guys? Have you tried to graph something? What does this formula just see? But can it graph things? I think so. What do you have to put in, though, to get graphs? Yeah. Yeah. Oh, that's really sad. Who are you? Oh, it's someone's card. I'm going to update your operating system. Is that okay? We'll see if we can get you back some programs. Does anybody else calculator when you hit the applications only show finance, like things got deleted accidentally? I'm going to start with this, Gavin, and see if this works. Nope. Okay. Then let's do send apps. Receive. Tony, yours is all gone? Let me see if I can get it. Oh, you only have weird ones. That says done, that says waiting. Let's try again.
Today? What did you guys do yesterday? Watch a video. The same one? It's
Might take a while. Why don't you guys on with the others, and then I'll try to update Gavin's and see if it works, and I'll update yours, Tony. Okay, so everyone else, you were able to find conics if you had a newer calculator? Okay, so you tell me, what do conics do? Okay, what about circle, ellipse, hyperbola? Let's say you hit on the, no parabola though? Okay, hit on parabola. What does it tell you? What does it show you? Equations. Okay, what equations does your calculator give you? We're under the, is it just called conics? Okay, in our TI. Under parabola, it gives us equations, and those equations include, for people that can't see it, or for people that don't have it, or for people whose calculators are trying to get it. Sadly, any calculator with the yellow button, yours was built with a different programming language, so there is no way for it to communicate with the updates, which is really sad. But for any of you whose calculators are at least this version, doesn't have to be blue, can be gray, yours can be updated, so that's kind of nice. Actually, Gavin, they'll probably update. Were you having it type out the NCR, NPR too? Oh, wait, no, mine does that too. I don't have the updated. I guess we could try with theirs, but I'm not sure if it'll be able to communicate with this one. Let's start here. So we have option 1, and we have option 2. Option 1 is y minus k squared equals 4p x minus h. And option 2 is x minus h squared equals 4p y minus k. What are some things that you recognize just now looking at these equations, these two basic equations, according to your calculator, of parabolas when considering them as conics? Are these normal based on like last semester stuff? They're normal? What's new? What's different? The p's, like, that's new, that's different. And also, hold on, last semester, did the squared come first? I don't think so. Didn't we have like y minus k is equal to a x minus h squared? Wasn't that our standard form last semester? I mean, or we could have gotten the y by itself and had a times x minus h squared plus, our forms didn't look like this. But what is the same? Do we still have k's and h's showing us like translations? So we still have h's and k's. The h's always go with the x. The k's always go with the y. So we're going to be able to say that our vertex is going to be hk. You guys remember parabolas? They're the little cups, the concave up, concave down. Or concave right, concave left. Ooh, we didn't see that last semester. We were looking at parabolas that were quadratic functions. So hold on, do you guys have little pictures, or could you make a picture with that parabola function? I want you to make one of this guy, y minus k squared, and tell me what he looks like, or whether he's vertically oriented, going up, down, or horizontally oriented, going right, left. Kyle, go ahead.
Would
mode matter?
Not unless you were plugging in a trig function.
And I'm getting 2p over 1 minus e cosine theta.
Change to function. If anybody else is in polar or parametric, you might want to go back to function, or sequence, go back to function. There is a form of conics, but it shouldn't make a big deal, but yeah, polar and parametric could change things up a bit. Didn't even know it did that. That's good for me to know for future sections. Anyway, coming back.
Number 1 sideways.
Sideways? Yeah, because the ones that we were seeing last semester, y equals x squared, oh, that was going up, wasn't it? So we're going to have parabolas, parabolic, but we're not just going to have up-down ones like we saw last semester, but also side-to-side ones. But hold on, you guys also noticed, or you stated, at least a couple of you, that this is new. True? And this is new. True? However, what did we have before that kind of meant the same thing? Kind of. Now, I'm going to have to change colors because it's not in the same spot. But didn't we have a multiplication? Oh, that's dark. Sorry. Didn't we have a multiplication before? Oh, it's going to be the same color. Yeah, we had a multiplication before, but our multiplication was here. Now, here's my question. Is A equal to 4P? Why isn't A equal to 4P? Where's A?
In front of h, x.
Right?
Yeah, it's with the square.
A is with the squared, but where's 4P? Not with the squared. Now, if we know how to get this, because we're going to review, and hopefully our brains will kind of complete the square, get back to here. It's okay. I want to see if you guys would agree. If we could get to like what we were used to, could we make it look like this? There's purposes as to, I mean, the P has a meaning, and you'll see it before the end of the section today / Monday. But could we make it look like this? Well, hold on. Both of these are actually going to this one, right? Both of these are actually going to this one. So let's start with this and say, okay, I need this to look like that. Someone tell me something to do to make it look like that. Minus k. Okay, I can subtract k. And can I subtract k and like flip them? Is that okay? Okay, so I'm going to write a times x minus h quantity squared equals y minus k. Do we see where that came from? Okay. Now what? Well, this gets confusing. How do I? Now what? Dividing is the same thing as multiplying by the. So who is 4p? Not A, but it is. We take our standard form, and if we rearrange him just a little bit, we can get to this new form that supposedly has some sort of meaning that we're going to have to use. Okay? All right, let's get into notes. Well, okay, we already did. We already kind of talked about, like, I don't know, there's a double-naped cone, and we're, like, slicing stuff, and things happen. The slices that come, oh, a circle comes out, an ellipse comes out, a parabola comes out, a hyperbola comes out, a point comes out, a line comes out, two intersecting lines come out. Did you guys see these vocab? These ones are the basic conics, and these ones are the, those degenerates. Anyway, yeah. Don't start calling each other that, but you can start calling points and lines and intersecting lines that. Those degenerates. It's weird that a point and a line and two intersecting lines come out when normally we think of as being curved shapes, and these are completely not curved, which is kind of weird and yet true. But that's why they're also called degenerates, because they have no curvature to them, or they are not intersecting or including any curved portion of those cones, which is kind of weird. But do you guys see at the very, 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 very bottom? there is a standard form that actually encapsulates all of the figures up above. But let me just do a quick example, okay? If this was a line, just a quick example as how the standard form equation works. If this was a line, would you have an A, a non-zero A? If it was a line? No. So wouldn't A be 0? What else would be 0? C would be 0 because I couldn't have a squared. What else would be 0? And a line, y equals mx, but y and x ever be multiplied? No. Okay, so hold on. A would be 0. B would be 0. C would be 0. But could I have a x term, a y term, and a number? Yeah. So just because this is a standard form equation, somehow some combination of a's and b's and c's and d's and e's and f's make all of these, it doesn't mean that they're all non-zero. Right? For parabola, what could we have? Well, we could have x's, we could have y's, we could have numbers, we could have squares, but we couldn't have two squares at the same time because parabolas only have how many squared terms? Just one, the other's not, or just one, the other's not. So for a parabola, I'm not saying that this would have to be 0, but if that's not 0, he had to be, and if that's 0, then, if that's not 0, he would have to be. One of them has to be 0, and one of them has to be a number. So to get each of these, something special, something unique has to be true. Okay, so going back really quickly to what we know from last semester of parabolas. There is the standard vertex form of a parabola. Y minus k is equal to a times x minus h quantities squared, or, here's an interesting one, x minus h is equal to a times y minus k quantities squared. Orientations of parabolas. Thinking about these ones that are up above, we already talked about how hk is the vertex. A has something to do with, if the vertex is the shifting, the horizontal vertical shifting or translating, A has something to do with the dilation, whether it's being stretched or compressed. And it could technically, if it's over here, be seen as a horizontal stretch, but over here it could be seen as a vertical. Well, wait a minute. If this is like a 2, it'd be horizontally stretched 2, but if it was over here, wouldn't it be vertically shrunk by 1/2? Wait. Does horizontal stretching results in vertically shrinking? Oh, so for a parabola, if you horizontally stretch, you are vertically shrinking, or if you're vertically shrinking, you're horizontally stretching. Or if you're horizontally shrinking, you're vertically stretching. So do you see how we moved the A a second ago to be the 4P? Like either way you look at it, it's true, whether it's on one side or whether it's on the other. But orientations of parabolas, if the x part is squared, then either, if A is greater than 0, we're going to have a concave up with a vertex at HK. Or if A is less than 0, we're going to have a concave down, right, with the vertex being once again at HK. But if we have it oriented the other direction, x and y has been switched. Ooh. Well, not quite switched. It's not exactly an inverse. But kind of. The horizontal term has been switched with the vertical term. The x's have been switched with the y's. As long as this is around an axis, we could think of it as being the, well, it's a little bit weird, but being the inverse. But anyway, that's okay. We won't go too deep. If A is greater than 0, it'll be a right facing. And if A is less than 0, it'll be a left facing. So last semester we did see concave up. Remember CU? Concave up like a cup or concave down. But now we can also have concave right and concave left. Not that we really talk about it that much. But remember, we do have positive and negative concavity, whether it's facing up, down, or whether it's facing right, left. Okay, so with that, let's talk about why on earth there is this 4p thing, which really comes from this. We just basically divide the a to the other side. But why on earth would we do that? Why can't we just keep talking about the dilations, the stretching, the compressing, and just forget the whole P thing? Well, because there are more pieces to the parabola than you actually saw. And to be honest, there's a definition behind the parabola that you guys haven't seen yet, at least not from me. Parabola is a collection of points Parabola is a collection of points whose distances from are equal, or we could say a collection of points equidistant from a focus and a directrix. Now, it doesn't mean all those distances are the same in the sense of D1 does not equal D2, does not equal, if I was to keep going, D3 or D4 or D5, because as you guys can tell, as you get farther away from the focus, the length gets longer. But what is true is that the distance to the focus and the directrix are equal. Directrix is always a line. It's not an asymptote, but it looks like one. It's not an asymptote, but it looks like one. And how it's drawn. It is the entire line, so we could name it Y. Now hold on, we know who the vertex is. The vertex is HK, right? Okay. Where H is the, now this one's at, I realize it's on the, okay. But I just want to keep it general. So what if it had moved somewhere else? It would be HK. H is the X value, K is the Y value. So isn't the directrix some sort of K, Y value take away something? Right? So K take away some sort of distance. But that same distance, now if it was tick marks of 1, yeah, we could totally say 1, but what if they're tick marks of 2 or 5 or 10? We'll get back to that in a second as to what those tick marks are. But do you guys see how the distance from the vertex to the directrix and the vertex to the focus are the same? Okay. So if I was to get to the focus, it's a point, so it's going to have an X and a Y just like the vertex does. But do you see how the H is going to be, whatever X is of this guy, it's the same X as that guy? It hasn't moved left or right at all, right? It's right above. So it's going to have the same H. But now it's not K anymore. In this example, you're adding distance. And let me tell you what that distance is. It's our little dude, our little guy P. It's that little dude, it's that little guy P. Now here's the problem. Like, I wish I could just stop there and be like, okay, no big deal, memorize this picture, you're done. But the problem is, guys, can't a parabola also be facing down? If it's facing down, guess where the focus is? Let me show you an illustration of a focus. Hold on, I had the book open just a second ago. I mentioned something about a light bulb in a parabolic reflector. I mentioned just a moment ago a light bulb and a parabolic reflector. Light bulb. Back at Despicable Me, huh? Where is he? He's right over here somewhere. Not Despicable Me, the light bulb. Do you guys see a couple things on the page right now in your book? I want you to read this paragraph right here. One important application of parabolas is in astronomy. Radio telescopes use parabolic dishes to collect radio waves from space. Parabolic. What else is parabolic besides radio telescopes or radio dishes or cable dishes?
Whoa, that was shaped like that.
with like the big old thick, and then you can like unscrew and the little light bulbs right there. You can see it. What shape is that flashlight on the inside? A parabola. But why? Because if the light source is put at the focus, the light will reflect off the parabolic to channel all the light in one direction. So wait, what's the difference between a lamp and a flashlight? What's a lamp do?
It illuminates it.
The light's there and just whoosh. Or is there a lampshade that keeps it from like going straight into your eyes? Yeah, it protects you. But does that necessarily channel the light? Well, kind of. It kind of channels, a lampshade kind of channels the light. Oh, it's kind of parabolic too. Kind of unsafe if it was totally covering the light. But lamps illuminate out, right? But what do flashlights do? Whoosh. And how does it zone in? Now, you guys can read more about reflectors in the sense of like there's a paragraph. There's some more stuff down there. But do you see an application of a focus? Figuring out a distance. Now, guess what? Wait. If the concavity changes, if it gets narrower or if it gets broader, guess what also changes? Where the focus should go. So we're not doing all of this necessarily application-y stuff right this second, right now, but what I'm trying to tell you is there's a point for this focus. Literally, the focus is a point. But in order to get to the focus, we need to figure out this guy P. Well, hold on. We already figured out this guy P. Isn't all of it, aren't we just taking the standard form and dividing the A? Oh, so maybe he won't be too hard to find. The only problem is 1 over A equals 4 times P. Will we have to do a little bit of solving to get there? Yes. We will have to do a little bit of solving to get there, but it is very possible to get there. My visual people, it's going to be really helpful to figure out who's being squared and what orientation, what concavity is going to happen as a result. Either up or down, it depends on what this coefficient is. Or if the y is being squared, it's going to be really helpful to think about, once again, the orientation, and then think about the positive or negative as to which direction, because if you're the focus, you're always inside the concavity. If you're the focus, you're always inside the concavity. And if you're the directrix, you're always outside, never intersecting. Do you guys see it? Just a little bit? If you're the focus, you're always going to be inside the concavity. That guy's a little too close. If you're the directrix, you're always outside, which means, depending on what's going on, if my x is being squared, if I have a vertically oriented, we could also say something about like a vertical axis. I can say my focus is always going to be keep the h. The k either has to add or subtract p, depending on whether I'm concave up or concave down. And if the y is being squared, hence I have a horizontal axis of symmetry. You guys remember the axis of symmetry is the guy that goes through, right? I can say something like, keep the k the same and add to the h plus or minus p. Ooh, do you guys see there are going to be some formulas? Whew. We're going to see the rest of the formulas on Monday. You guys might want to start playing with homework this weekend using the examples in the book, because it's going to get a little tricky. But you have options. You can either memorize all of these pictures or try to find the patterns and understand how to work them yourself. Patterns or pictures? Did it finish? Did. Let's see if it worked though. No, all that work? All right, Gavin, let me keep playing with it. I'll see if I can get them for you. I had to update first before it would accept it, so now I'll try. Come back at lunch.
Okay.
Does that sound good? How do I send my apps?
Honestly, I don't see him to school on Wednesday.